Okay, today's class we're discussing limiting reagents and theoretical yield. Theoretical yield is the amount of substance formed when all of the limiting reagent is used. And you can calculate a theoretical yield mathematically from the balanced equation. But you have to have the balanced equation or else you'll get the stoichiometry wrong and the results will be, from your calculation will also be wrong. The actual yield is what you actually get from the reaction, because in real life most reactions don't go to completion, so they give less than the calculated stoichiometry would predict, and that gives rise to the notion of a percent yield. A percent yield is the actual yield divided by what you calculated you could get times 100, so that gives you a percentage. And as an example, we took an example from the textbook Zumdahl, 8th edition, on page 113, where he asks methanol, and I'm paraphrasing, methanol is a potential fuel, 68.5 kilograms of carbon monoxide is reacted with 8.6 kilograms of hydrogen gas to form methanol in an industrial process. If 3.57 times 10 to the 4 grams of methanol is produced, what is the percent yield for the reaction, for this reaction? So what we had to do first is show the balanced chemical reaction. Carbon monoxide combines in the ratio of 1 to 2 with hydrogen gas to form methanol. And the first step of the calculation is to find the theoretical yield, and that we do by finding out which one of these two reagents is going to finish first. So we divided the molar mass of carbon monoxide into the mass that was available, and find out that we have 2.4 times 10 to the 3 moles of it. We find out also using the same technique that we have 4.26 moles of hydrogen gas. But because they're in the ratio 1 to 2, what that means is if we have 24 moles of carbon monoxide, we're going to need 48 moles of hydrogen. What we have here is 2.4 times 10 to the 3 moles of carbon monoxide, and we're going to need roughly 4.8 times 10 to the 3 moles of hydrogen gas, but we only have 4.2. What that tells us is that hydrogen is going to be finishing first. Hydrogen is the limiting reagent. It stops the reaction because it runs out. So we begin our calculation from the limiting reagent, because we want to find out how much methanol is going to be produced. And I illustrate that here by saying that the stoichiometry of carbon monoxide and hydrogen is 1 to 2 in this reaction. There are roughly 2,400 moles of carbon monoxide, which requires 4,800 moles of hydrogen. But only 4,200 moles of hydrogen are present, therefore hydrogen will run out. And I show that mathematically. Here's the actual number times the stoichiometry. That's how much hydrogen is required. So we know what we've discovered from this point is that hydrogen is the limiting reagent, but we can't continue the calculation from there. We have to start our calculation from the number of moles of limiting reagent. In this case, that's how many moles of hydrogen we have, and we incorporate the stoichiometry of the reaction. For every 2 moles of hydrogen gas that's reacted, we'll get 1 mole of methanol. So that predicts that we're going to get 2.1 times 10 to the 3 moles of methanol. I multiply by the molar mass of methanol, and we obtain that there are 68,000 grams of methanol produced, roughly. We report that to 3 significant figures. You notice this is 3 significant figures because there's no decimal place after the 0. So you only count these numbers. You don't count the zeros because they're spacers. There are 3 significant figures in this answer. So then we calculated the percent yield. The actual yield was 35,700. Put that here. And the theoretical yield was 68,347. You'll notice I put the unrounded number there to continue the calculation. We got 52.232, and that rounds down to 52.2% yield.